All right, we're back talking about automatic pitch tracking. And we have the basic concept down at this point, I think, where you basically are trying to figure out what's the fundamental period of a complex wave like this. And we use these mathematical tools like calculating the R value between different chunks of a waveform. We take the two chunks which have the best R value or the highest R value. We figure out what the period is, what the time difference is between the start of one of those chunks and the next. And we use that period, we take the inverse of it to figure out what the fundamental frequency is. And so the question is, how many different periods should you look at when you do this? And I guess one theoretical answer you could give is all of them, at least as many as might possibly fit into the waveform from here until the end of time. But doing something until the end of time might take you a long time. So I'm not sure if you really want to do that. And then instead, Prot or any pitch tracker really will look at a limited number of possible periods. And the default frequency range setting in Prot when it does pitch tracking is to go to 75 hertz on the low end to 600 hertz on the high end. And you might be able to remember, we talked a little bit about why this would be so in 341. If you recall, we talked about typical or average pitch values or F0 values for men, women, and children. Average adult male F0 is going to be around 120 hertz, something like that. For females, it'll be like 200 to 220 hertz. For children, it'll be like 300 or so. And that's average value, so it's going to go a little bit above and beyond that. And for Prot, the answer is to kind of take this range, not knowing who a speaker is before you analyze it. 600 hertz is probably pretty high for most adult speakers, although female speakers will tend to get up in this range more often than men. 75 hertz is actually fairly low. You rarely hear anybody get below that, which is why it makes kind of a nice default lower end. You can, however, set this to different settings as you go, and I'll talk about that more later. I also want to point out that when I'm talking about 75 hertz, the period I'm checking for that is 1 over that, right? 1 over 75 seconds, basically. So if it's 600 hertz, the period of that is 1 over 600 seconds. I don't know. I can't translate that into decimals right off the top of my head. Something like 0.001667 or something like that. But it's a small number, right? So that's what we're talking about when we're looking at these periods. Okay. So I want to point out that having figured out what the fundamental frequency is at time 0, the very beginning of this waveform, the next thing the pitch tracker would do is move on to the next sample or the next step, however you define that in the pitch tracker, and then figure out what the pitch is at that particular point in time as well. And then it would go through this entire comparison process again, where it's picking other windows down the line to figure out what the period is from here to wherever, right? So it has to do that going through the entire waveform, which is why you don't want to have processes in here that take you forever to do, basically, because it's got to repeat a lot. You want this to be relatively efficient. Lucky for us, with modern computers, it's relatively easy to do this very quickly. And ultimately, what we get out of that is a pitch track. This is a example I borrowed from a friend a long time ago.
I would like a flight to Seattle from Albuquerque.
Which is a nice example of what is called uptalk in modern English intonation. But this is the pitch track you get out of it. This is a phone call, so the spectrogram is cut off at 4,000 hertz due to the low sampling rate, but it sounds like this.
I would like a flight to Seattle from Albuquerque.
And it's kind of fun because it's a statement, but she's raising her intonation at the ends of each one of these little phrases, making it sound a little more like a question, but maybe not exactly. We'll talk about that more later as well. There's a little boo-boo. This should be 75 hertz here. I changed the lower end to be 60, but you can see that even with this speaker, whose F0 goes up pretty high, it's easily encapsulated within this entire range of Prot's default settings for frequency range. The other point is you can also see with this representation these little points, these little dots, where it's calculating the F0 separately for each dot. And if you want to, you can draw a curve to kind of smooth it out. But this gives you a sense that it's making these calculations on a sort of repetitive basis throughout the entire waveform. Okay, so hopefully you've got a sense of how this works already, but I want to dig into it again using a specific example, using a part of a recent voicemail message from my mom. And the reason I'm doing this is because I am going to ask you guys to do some pitch tracking in a very basic, simple way using numbers in an Excel spreadsheet for your first homework, for your digital signal processing homework for this class. So just to make sure I can get the algorithm across to you well, we'll look at it in a slightly different way using this sample.
This night is going to be about Norwegian and German farmers coming to the Midwest. Well, anyway.
Yeah, so that's my mom. She and my dad are retired at this point. My mom came from the East Coast. My dad grew up on a farm in the Midwest. And as my dad has gotten older, he's become more interested in his heritage. And each night, my mom and dad watch a movie. And this is just her description of the particular movie that they were going to watch that night.
This night is going to be about Norwegian and German farmers coming to the Midwest. Well, anyway.
So suffice it to say that my mom is not as enamored of the Midwestern farm culture as my dad is. But be that as it may, this gives us some material to work with for our automatic pitch tracking analysis. So what I've done is I've taken a little snippet here. You actually can't hear it here because my PowerPoint doesn't want to play super short tokens. I'll just play the snippet here. Yeah, it's in that about that she mentioned in the initial token. And so what I've got here is a little chunk which is from 1.85 seconds to 1.9 seconds of the sound file. We'll talk about this a bit later, but this is about 0.4 seconds, a window of the size of 0.4. That's the window size that Prot looks at when it's doing automatic pitch tracking. So you can see there's multiple repetitions of the complex waveform in here. We can see the glottal pulse spikes at the top. There's a lot in here, and we actually can kind of eyeball this. So we got 1, 2, 3, 4, 5, 6, 7 repetitions, and then some change. We know that it's 0.4 seconds long. So we could say, well, how long does each repetition last? We've got 0.4 seconds, and we are able to get 7 repetitions in there. That gives us about 0.057 seconds for repetition. So that's about the period, just eyeballing it. And then if we take the inverse of that, I messed up something there. Never mind. I think I should have said 0.04 divided by 7. Take the inverse of that, 175. Sorry about that, class. We can expect the F0 of this to be somewhere in the vicinity of 175. So anyways, let's just pretend that I didn't do any of that and let the computer take over for us, because I think that may have done nothing but mislead you. So I'll mention before we do that that this is a phone message. So the sampling rate of this is only going to be 8,000 hertz because my mom is traditional in her own way and still likes to call on landlines. All right, so let's get our bearings here a bit. So the default frequency range in Prot is 75 to 600 hertz. What's the period of a 75 hertz sound? We talked about that a little bit ago. And that is going to be 1 over 75, right? And if you actually work with your calculator the right way, that'll tell you that it's 1 over 75 is 0.0133 seconds. What's the period of 600 hertz sound? We can calculate the same way. It's 1 over 600. And I think I mentioned this a while back. But that, in terms of decimal notation, is 0.001667. Okay, so just to reiterate a point, in case you've forgotten it or in case it's still not clear, but if you have longer periods like this, it's going to give you lower frequency like that. And higher frequency sounds have shorter periods. Higher frequency sounds repeat more often, so their periods are short. Lower frequency sounds repeat more slowly, so their periods are long. Okay, so the way this is actually going to work when Prot might have a go at this is that its pitch tracker is going to look at all the potential fundamental periods ranging from this amount of time on the short end to this amount of time on the low end. So the closer we get, we take an initial chunk, the closer we get to that, and starting our second chunk, we're talking about higher frequencies. And as they get longer and longer or further and further away from the beginning of that initial chunk, we're going to get analysis for lower frequencies until we get to the end of how far we want to look at. Okay, so this is, if we actually do this for every single possible frequency between 75 and 600 hertz, it would take a long time, at least if we're trying to do it mentally by looking through these slides. So I'm going to simplify things a little bit and just say, let's look at only 3 possible frequencies within that range and see how it shakes out. So our overall range is 75 to 600 hertz. Let's just look at 100, 200, and 400, in part because those 3 frequencies will make the math relatively easy for us. Okay, so the period of 400 hertz sound class is just going to be what? 1 over 400, right? And that winds up being 0.0025 seconds. Likewise, so the reason I wanted to mention this is because now we can kind of get a sense of how many samples we have to look at. So in this token, we have an 8,000 hertz sampling rate. So there are 8,000 samples in a second. The token itself is longer than a few or more than 1 second. But for our windows, for our purpose, I'm trying to figure out whether or not 400 hertz is the actual frequency of the sound at some point in time. I want to look at a period of 0.0025 seconds. In terms of samples, that means we're dividing 8,000 samples by 400. And so that period would be 20 samples long. So there'd be 20 samples between where our original waveform begins and where we expect a sound with an F0 400 hertz to start a new cycle. Hopefully that makes sense, but if it doesn't, just walk back through the math and make sure you can get it. We have 8,000 samples per second. We have a period of 0.0025 or 1/400th of a second. So for this potential fundamental period, it would look like it was 20 samples long in our waveform analysis. Likewise, we're going to check 2 other frequencies. We're also going to check for 200 hertz. So in that case, you'd be dividing 8,000 by 200, and you'd get a period of 40 samples in the waveform. That is equivalent to 0.005 seconds or 1 over 200 seconds. And lastly, we have a 100 hertz sound. This one's kind of the easiest. Its period will be 1 over 100 or 0.01 seconds. For that one, to figure out how many samples there are in the period, you divide 8,000 by 100, and you get 80 samples in the waveform. That's the gap between where your initial chunk begins and where your comparison chunk is somewhere down the line. Okay, hopefully that makes sense. I'll show it to you visually. So let's look at 400 hertz first. That, again, is the highest frequency, which means that it has the shortest period. And as we figured it out here, that means there's only going to be 20 samples in the period for 400 hertz. This is what the initial waveform looks like for a 400 hertz wave. The start of the comparison chunk is going to be blue here. So this is where our initial window begins at the 0 point, or the 1.85 point time-wise here, really. 20 samples later, we're at this transition between the orange and blue. And I actually simplified this a bit. This blue chunk should actually extend a little bit further over here, but to make this the exact same width as this initial graph, I've cut that out, but it will factor into the actual calculations. But this blue stuff is our comparison waveform, and this orange stuff is our initial waveform. And we're trying to figure out what is F0 at this point. Is it 100, 200, or 400 hertz? So to do 400 hertz, to calculate that, I'm lining up these 2 chunks, and we can kind of eyeball this again. So actually, go back slide. So remember our first chunk, we're starting low and going straight up, and after a little bump, we go to the big bump, and you can see that here, blah, blah, blah. And for our blue chunk, we start low, but then we go down, even further down to a valley, and then we pop up to a kind of medium-sized bump. And you can see that here, right? So we start low, go down, then bump up to a medium-sized bump, and then don't get to a big one until we're somewhere a few milliseconds into the waveform. So eyeballing it, like we did before, you can see, well, these big peaks aren't really lining up with each other that well. This one is in the middle here. This one is in the middle there. We're not getting the timing particularly right. So we can kind of guess it's probably not going to be a great match. But basically, we're going to multiply this sample value by this sample value, blah, 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 all the way down the line. If you look at this in terms of like an Excel spreadsheet, this is the way the math would work out. So for our original chunk, the first sample is in sample 14,800 of the whole waveform. That's at time 1.85. This is its amplitude value. This comparison chunk, remember we're looking 20 samples down the line. So it's at sample 14,820 or time 1.8525, so on and so forth. It's this amplitude value. It coincidentally happens to be the exact same amplitude value as that one. You multiply them together and you get 0.024. For each window, you move to the next sample. This one is this amplitude value, negative 0.009. This is negative 0.269. Like I said, for the blue one, you go down. For the orange one, you're going up. You can see that in the numbers here. If you multiply these two by each other, you get a product of 0.002. Again, thinking about this mentally as human beings, it gets very boring very quickly because we have to do this for 320 different samples, right? Over and over and over again. Each time, this comparison chunk sample is going to be 20 samples down the line compared to the original. If you do that, calculate the products for each lined up pair of samples, and then add all those products together, you wind up getting an R of negative 0.25. I'm not going to walk you through all 320 calculations, but hopefully you get the idea. Also, hopefully you get the idea that this is not a great match because we're in negative territory again, like we saw before. So that doesn't look too good, but we're just getting started, right? So that's our first potential frequency. This is try number 2. We want to look at 200 hertz. I'm going from higher frequencies to lower because that means we're going from sort of shorter periods to longer. So we still have the same initial chunk here, and the 200 hertz wave is going to start further down the line. So before we had a 20 sample gap in between the beginning of our initial waveform and our comparison waveform. Here we have a 40 sample offset, which translates to 0.005 seconds or 1 over 200 seconds, right? Because this is the 200 hertz wave that we're worried about. And before we go to the next slide, hopefully you can see these look like they match a little better. So remember, this one is negative, it goes to a little bump, then a big bump, and then through the complex wave. This one's negative, not quite as negative, but goes through that little bump to the big bump, and then goes through a similar complex wave. So this looks like it's going to be a better matchup, hopefully. We can take a look at it here, and kind of the crucial thing again, or the easiest thing to see here for us, is how well these big bumps line up with each other. And they're looking like they're pretty close in time, right? Okay, so again, for the math, the way the computer would look at this is it's just taking this amplitude value at 14,800 and then comparing it or multiplying it by the amplitude value from 14,840. 40 samples down the line because we're dealing with 200 hertz frequency. And the products there, well, these aren't that impressive. These are relatively small numbers, and we don't have enough samples to get to these big peaks, but they're all positive. And in fact, if you walk through again all 320 of these, the overall match looks better. It's R equals 6.21. So that's a lot better than that small negative number we had for 400 hertz. Okay, so that looks pretty good. We can also try the 100 hertz potential frequency. And again, the beginning of this one is going to be offset from the beginning of our original waveform by 80 samples or 0.01 seconds. And if we do that, we actually wind up in kind of a similar spot as we were before for the 200 hertz waveform. So we're starting low, we're getting through this little bump, then going to a bigger bump. It's not, again, a perfect match, but it looks like we're kind of in the neighborhood, right? So who knows what we're going to get out of this. We can also kind of eyeball it. These big peaks look like they're fairly close again. Maybe a little bit offset, maybe a little bit of difference in the sort of complexity that follows the big glottal pulses too. Either way, the computer doesn't care about looking at it. It looks at it by doing the math. So it's multiplying that amplitude by that amplitude to get this product, that amplitude by this amplitude to get this product, adding all these products together. And what you wind up getting is an R of 2.55. So it's also positive, looks relatively good, but it's not as good as the correlation we got for 200 hertz. So if we're only considering these three candidates, if we're only considering 100, 200, and 400, then we say 200 is the winner. It has the highest R value. So we say at this point in time, the fundamental frequency of this waveform is 200 hertz based on that tiny little analysis. And hopefully that makes sense. Ultimately, what you have to do after this one is take a step somewhere down the line, whatever your step size might be, and say, I'm going to calculate F0 again. Maybe it's going to be slightly different this time. Okay, so the big picture is sticking with this initial spot, and in this three possibility analysis, we decided it was an F0 of 200 hertz. If you actually run that analysis the way the Prot pitch tracker runs it, for every possible frequency candidate between 75 and 600 hertz, it turns out 200 is pretty close. 195 is the one that actually gives you the best match. And I think when I did that garbled calculator analysis before, I was hoping to get to 175 just based on eyeballing it. So yeah, there's a reason why that was pretty close. This is a graph of all the R values for all the different potential F0 candidates. So that might be hard to see here, but we have 75 hertz at this end, and we have 600 or 615 actually is the way it works out technically at this end, and it goes from high frequency to lower frequency down here. And again, this might be hard to see, but just because of the way the math works out, you can check a lot of the different lower frequencies when you do this, but there's a bigger gap between all the various high frequency options you can look at. So it goes from like 615 to I think that's 533 to 471, 421, 381, so on and so forth. But on this end, it's like 75, 76, 78, 79. Either way, our best match is here. This is the highest R value for all these different potential frequency candidates. It's 7.68, and it's at 195 hertz. And what you might notice is there are kind of interesting patterns in here. And one of those patterns is that the second best candidate is at 98 hertz, which is basically half of 195 hertz. And so having recognized this, so this is the second highest R value, not quite as high as this one. But I want to ask, why do you think that is? Why is our second best candidate half the frequency value of our best candidate? And I'm also going to ask, what if we had set our frequency range differently in our analysis? Here we're using Prot's default from 75 to 600. What if we had made our highest frequency that we check in the analysis 150? And so we're just looking at this range of frequencies here. What would happen when we actually ran this through Prot? I'm going to pause there, let you think about the answer, and then I'll come back with what I think the answer is in the next video.